Hello there, colleagues. I am doing a video for week 3 feedback. I want to take just a little bit of time to talk about the null hypothesis, particularly a null hypothesis for directional hypotheses, and then also kind of demonstrate some of the challenges that we're having with the confidence interval and why it matters, because I think I can show you mathematically why this is a potential problem and why my hair was on fire when we discovered what Salkind was doing to us. Anyway, we'll get there eventually. I want to start with the hypothesis testing. So I know this looks a little pixelated, but there's just recently, as of yesterday, someone from Hollywood who made the claim that she made a racist remark because of the influences of Ambien. So when she tweeted that, well, the folks who created Ambien decided to tweet back, and they had a different theory. And so they, but what's clever about their response in their tweet is that they actually use the language of hypothesis testing and experimental design in their response. And so if you'll notice here, it says, while not all pharmaceutical treatments have side effects, racism is not a known side effect of any Sanofi medication. So there are a couple of reasons why I love this snarky remark, partly because it's snarky and I'm down with a snark, but also because they found a way to make their snarky remark using the language of hypothesis testing. So maybe that will help us have a little bit of fun with the question of directional hypotheses. So let's first take a non-directional hypothesis set. When we're talking about a set, we're talking about a hypothesis and it's null. Okay, so we have a non-directional hypothesis set here, which we have a hypothesis and it's null. The hypothesis is there is a difference in racism scores between persons who take Ambien and persons who do not take Ambien. Now, this is non-directional. I'm just saying there's a difference. I didn't say that the scores are higher or lower. I just said they're not the same, right? And so the null hypothesis is they are the same. So in the case of the alternative hypothesis, the sample mean will not be different than the population mean. However, in the null hypothesis, the sample mean will be the same as the population mean. Now, since I'm doing a non-directional hypothesis set, that means that not the same portion of probability is actually spread on both sides of the bell curve. Half of the probability is on the right and the other half is on the left. So let me show you a picture of this. Here you see a normal bell curve. We've split our p-hats into two groups. There's a group on this side and a group on this side. In the center, in this white area that I'm outlining, that is, let's say, 95% of the population would be surrounded somewhere around this mean, right? This purple part on the right would represent 1/2 of our p-hat value. In the case, this is 95%, this is 2.5%, and this is 2.5%. Okay, now I can represent that. Let's take the bell away and just look at the probabilities. And you can see in this diagram here we have two samples, the sample of persons who took Ambien and the sample of persons who did not take Ambien. And we have their scores on a pretend racism scale. So the persons who took Ambien scored a mean of 80 on a racism scale. People who did not take Ambien scored an average or a mean of 50 on the racism scale. But look here, we have some probabilities that are distributed on the lower part and on the upper part of the range. So there is, we're expecting that a 2.5%, if this is 95% in the center, then a 2.5% is on the right side and 2.5 is on the left side. Okay, so the thing about a non-directional hypothesis is I'm saying it's different. I don't know if Ambien is higher or lower. It could be that Ambien is lower than no Ambien. Let's look at the difference between 50 and 80, the mean of 50 and the mean of 80. And so here we can see that where these cross over one another, you can see that some of the confidence interval, it represented in the blue here, some of that confidence interval is the same as some of the confidence interval in the no ambient sample, which means that they are not different. Now, I took math in second grade. I remember 80 is bigger than 50. You can probably figure that out too, but statistically, they are the same. So let's go back to our hypothesis test. We said statistically, is there a difference between racism scores? And if they are statistically the same, here we are failed to reject the null hypothesis. We see that there is crossover in the confidence interval. Well, let's look at another example in a place where we do see a significant difference. In this case, we have a score of 80 compared to 50. And so in the previous one, 80, 50, let's say I guess we have more in our sample this time. The n is bigger because the means are the same. But anyway, in this case, we're looking at our confidence intervals, and the edge of this confidence interval and the edge of this confidence interval, we don't see overlap in the blue. Do you see that? We have the overlap is purple. And so that 2.5% on this side and the 2.5% on this side are overlapping. And because they are the parts that are overlapping, we are going to say that they are significantly different. So that's it's really a question of whether our confidence levels are overlapping one another or not. Well, here's the deal. A non-directional hypothesis just says they're different. In a directional hypothesis, let's say for some reason we have a sneaking suspicion that persons who take Ambien do score higher on racism scales than persons who do not take Ambien. So we want to say yes, or we want to test whether it is in fact demonstrable that persons who take Ambien score higher on a racism scale. So this is a directional claim, right, or directional hypothesis. So the opposite of that is not less than, it is less than or equal to, right? So do you see here that if the alternative hypothesis is greater than, then the null hypothesis is less than or equal to. Less than is interesting, equal is really important here. And I'll show you why, because it'll relate to our non-directional hypothesis testing that we did a moment earlier. But let's look. In this case, we have stacked all of our p-value on one side of the curve. And so we don't care about probabilities on this side, right? It's not meaningful. All of our probability is stacked over here on this side. So this is 5%, and then this is 95%. All this white area is 95%. And this is 5%, not 2.5 on each side, 5 on one side. That's a directional hypothesis. Well, there's a theoretical reason for choosing a one-tailed hypothesis set. Now, in this example, it's a little bit silly, and we're kind of goofing off. But if you let's imagine that we were looking at cholesterol. And what's the mean cholesterol for a sample who eats fettuccine Alfredo every day compared to people who only eat vegetables? Well, we would expect that the mean cholesterol for the people who eat fettuccine Alfredo every day would be higher. It would be bizarre and meaningless if it were lower, right? So we're really only testing whether it is higher. So you might think that Ambien and non-ambien being equal to one another means that they have the same mean. Well, that would be a way in which it would be equal. If they had the same distribution and the same mean, they would be equal, and they would be literally equal. But statistically equal can also look like two different means. In this case, the Ambien score is lower. We expected it to be higher, and that's why we chose a directional hypothesis. But our null hypothesis is supported here. We have failed to reject the null hypothesis because our Ambien score is lower than the non-ambient score. But that is not merely lower. It is also equal to. And the reason I know it's equal to is our confidence intervals are shared. Do you see that? This is a different example. In this case, the ambient score is higher than the non-ambient score, right? But it is not significantly higher because our confidence intervals overlap with one another. And since our confidence intervals are overlapping with one another, statistically, they are equal. So let me go back and show you again. We'll stop here at the directional test and say if they are less than or equal to, then we're going to say that we have been unable to reject the null hypothesis. But let's take a second and go back to that non-directional hypothesis set. Here, we said that when there was no difference in racism scores, that the mean is equal to the population mean, that they are equal. Even if they're not the same number, statistically they were equal. If they're different, they're not equal. So, coming back to our directional hypothesis set, in this case, if it's not greater than, it is either less than or equal to. So when you're doing a directional hypothesis set, you'll have a direction for the alternative hypothesis, less than or greater than. Your null hypothesis would be equal to or the opposite, right? So if you find that the means are the same in terms of probability as we have here, then we're actually finding that we failed to reject the null hypothesis. In this case, however, it is clear that 85 is statistically higher than 60, and so it is no longer equal to, because we have moved into this band of probability, now we can say that we can reject the null hypothesis. One other thing I want to point out here is that, as you can see, our p-hat value is much wider. If we were doing non-directional, this probably would not show up as significant. But because it is directional, our band is wider. It's 5% all in that one spot. We don't have 2.5 here and 2.5 on the other side. And since we have 5% all here on the one side, then it is significant. So one of the challenges is identifying what your hypothesis is and identifying whether it should be directional or non-directional. If you have a theoretical reason for it being directional, you may discover that you have significant findings when you wouldn't have had a significant finding if it was non-directional. Okay, so let me talk for just a moment why my hair was on fire. Last night when we were talking back and forth on email and comments and texts and phone calls, and thank you so much for the feedback. I really appreciate you helping me see where some of you were coming up with a very consistent formula, and sure enough, it was right there in Salkind on page 193. So Salkind suggests that one way you can test for confidence intervals is to take the mean plus or minus the z-score times the standard deviation. Okay, so for the first of the two examples on the third prompt, that would be the mean was 80 plus or minus 1.96 is the z-score for 95%, right? Times 2 standard deviations. Well, so under Salkind's formula, then you have 80 plus or minus 3.92. Now let me show you why my hair was on fire. Everybody else, I looked in every one of my books, I looked in a whole bunch of places across the internet, of places I trust. Everybody agrees that the formula for confidence intervals is the mean plus or minus the z-score for the probability that you're looking for times the standard error, not the standard deviation. And so over here is the formula for the standard error. That can sometimes be represented as the square root of standard deviation squared divided by the n. That's the standard error formula. And so in this case, that would be 80 plus or minus 1.96 times 2 divided by the square root of 70, which is our n. And in that case, you end up with the confidence interval of mean of 80 plus or minus 0.47. Now remember how a few minutes ago I said I went to second grade? I know 0.47 is a lot narrower than 3.92. And in fact, this is how everybody I know who measures confidence intervals measures confidence intervals. So when Salkind says, well, check with your instructor, I don't know what Salkind's talking about. Now, I did not write a textbook on statistics, so maybe I just don't know what Salkind is talking about, but I don't know what Salkind's talking about. And so you can kind of see why I might be freaking out a little. I also want to show you why this matters. If we said that the confidence interval is defined by Salkind, Salkind is going to have a much broader confidence interval. Do you see that? Much broader. And because it's much broader, you're going to end up with a lot more type 2 errors because you're going to require so much change in order to find a significant finding. The significant finding should be defined by the standard error. I just don't understand why Salkind said what he said. I really think you should think about understanding it in terms of the standard error, like every flippin' body else. I hope you have a great week. If you need me, don't hesitate to give me a ring or schedule some time with me for a one-on-one. I'd be more than happy to meet with you. Hope you have a great week.